Chapter 8, Combined Loading. Let's review an example in a circular foundation. So in this example, we do have a circular foundation, the diameter of D, as you can see in the figure, and handling a concentrated load at a distance of E from its centroid. If the weight of the foundation itself is equal to 3 times P, so we want to calculate the maximum E. What is the farthest distance of E in which all the foundation remains at compression zone? Part B, the state of stresses at center, maximum, also a minimum. So let's see how we can approach our problem. So for sigma minimum, if we just transfer our concentrated load to the centroid and create a opposite of that to cancel that force, because in reality we just have this P at a distance of E, then obviously these two forces create a bending moment of y, which is the clockwise moment, which pushes a point here and pulls a point at sigma minimum. So this is sigma minimum, and definitely this is sigma maximum before any calculation. Sigma minimum is there. So for example, if this is our foundation and this is our soil under it, so you can easily see at this point there is a possibility that the foundation goes in experience a separation from the soil beneath. So that's we need to be careful about designing this point. That's our sigma minimum. That's a push of forces. Overall force by force means concentrated plus weight of a structure. That's a W3P. Just it's a general force. That's a 4P over the area plus a pool at that point is just a positive m moment over moment of inertia times the distance, which is d over 2 of diameter radius. And that's a threshold of separation. That's a threshold of separation of foundation from the soil, sigma minimum. If you replace the numeric value for that, that's a negative for a downward push. Weight of a structure and concentrated load, that's a P, that's W2. That's how we get this part over the area of solid circular foundation. Plus, that's a separation, that's a positive stress. And if these two are at the edge of separation, it means these two forces are equal, the stresses are equal. And that says if you equalize the two part, it just gives you that's our moment, P times E times distance, which is here. If you cancel out the terms, it just gives you an eccentricity of D over P. It just says the maximum distance, if you can locate force P, is just D over 2. So you can it all the way to the corner and yet not separate from the other side, which is sigma minimum. That's the edge of separation. It's not yet separated, so the equation of mechanics of material are still useful. You can still use them. For sigma maximum, as soon as you have calculated the eccentricity, which is d over 2, a sigma maximum happens here, which is a 2 push one from a normal force due to weight of structure and concentrated load, and the other one again extra push due to a moment which pushes the point at sigma maximum. So if you just take the negative out of the calculation, that's 4p over pd square over pi d square over 4 plus a moment times cp times d over, which we already calculated. That's all p times e, which is d over 2 over p pi d to the fourth over 64. And if you do the math, it just gives you a push of 32 p over pi d squared. That's all numeric value for or metric value for sigma maximum. And likewise, sigma at center, like if you just climb down the centroid of our structure foundation, it just gives you a there, because this moment doesn't create any any stress there, because for moment we need there is no distance to calculate that stress, so that m goes by zero, this terms goes by zero, and just have 4 pi, a push of 4 pi over the area of foundation. That's 16 times p over pi times d squared. Thank you. You'll solve more problems in foundation.